Daniel and we are going to share with you some of the work that we've been doing, but at the same time, trying to generalize a lot of the learnings from the work that we've been doing in the context of transfer learning, not just for vision, which you'll see at a lot of conferences. And we're going to show you that this general concept of being able to perform transfer learning is no longer just limited to vision, but applicable to many other problems from NLP systems to text, right, to even more recent work on machine reading comprehension. Right, and so hopefully this will be useful to you. Now, but before we get started, just want to get a sense of the general sense of the people in the room. How many of you are deep learning experts? Okay. How many of you are doing deep learning in some ways? And how many of you are doing deep learning on vision? Awesome. And how many of you are text NLP people, or you've been looking at that? Okay, fair amount. Right. So hopefully this session, for a while, Daniel and I has been doing a lot of sessions on this whole concept of being able to do the task of domain adaptation, but more importantly, being able to apply transfer learning, and why we think, and I think by now for many of you that are starting to get to know or getting into deep learning, you realize that transfer learning is really the dirty secret that no one will tell you about, but it's what actually makes you very productive, and it's actually the technique that's behind many of the APIs that the big tech companies are releasing. And therefore, we think that, hey, first by educating you about what transfer learning for vision is, it's going to give you that good head start. But more importantly, showing you how you can now apply it to many, many diverse domains is going to help. And so let's get started. Now, if you take any kind of data science course, machine learning course, and so on and so forth, this is essentially what you're going to see, right? You have a business problem, and you start choosing a learning task. But more importantly, once you have done that, you figure out what your data is, you perform a lot of data transformation on it, and then finally you choose an algorithm, right, or a learner. And finally you say, well, what are you trying to predict? You run it with different options, right? Some talks might educate you about what is hyperparameter sweeps and so on and so forth. You look at the end results, you debug and you visualize some of these results, and finally you apply it to some of the problems that you're solving. And this is a typical data science process, if you will, which you'll get out of many machine learning textbooks. Right? But today, if you're going to do industrial-grade machine learning solutions, you'll realize that, hey, data science is a great field to be in. Deep learning is a great set of techniques for you to apply, but industrial-grade ML solution that you get applied to your respective business applications, if you will, or startup that you might be thinking of, right, is not really just that one attempt, right? There's going to be many, many attempts that the data scientist doesn't tell you, and a lot of frustration and scratching of head, a lot of late nights before they get to a final solution, right? And today, when you start looking at deep learning in general, especially in vision, in traditional machine learning, you will explore different kinds of algorithms, if you will, right? So if you're trying to do classification, you might be doing decision tree, you might be doing support vector machine, you might be doing naive Bayes point machine, and all sorts of fancy kind of classification algorithms, if you will, right? And then you will start figuring out which one gives you better results, right? And same thing if you're trying to apply vision, right? You'll try the different kinds of deep learning architectures or convolution neural net architectures, if you will, right? From the very early AlexNet to what is today like ResNet or Inception V3, V4, and so on and so forth. And then you'll try to apply it to your different tasks, right? But transfer learning is really the whole notion that, hey, let's face it, right? We will not have the compute and infrastructure of many of these big tech companies, but yet we want to be able to create startup, or we want to create innovative application in our own area, right? But leveraging all this work that all these giants have done, right? And so if you look at one typical data set that we're going to share later called ImageNet, no one is able to train ImageNet using the infrastructure that you have or the laptop that you have, right? And therefore, you really want to rely on a lot of these tech giants, all these research labs, to be able to apply and create new innovations in training against large image data sets. And ImageNet today is relatively small compared to the larger image data sets that's out there. And then being able to say, well, you have spent so many days, and today you can actually do ImageNet training, the recent work that came out in July this year, in 4.4 minutes, which is fascinating. It used to take days. And then start applying the model that gets trained to the problems that you have. So for example, right, you could have take a pre-trained model, which is trained on ImageNet, right, and then start applying it to the domains that you have. It could be you're trying to classify whether there is a dent in the road that needs repair, or you're trying to classify, hey, there's a bird in the picture, and so on and so forth. And therefore, transfer learning is really that little secret that we want to share with everyone that allows you to apply a lot of this great work that has been done in domains of your choice, right? And what is also fascinating is if you look at transfer learning in general, and why are we talking about transfer learning, right? And if you look at the y-axis, which is commercial success, today we know a lot of supervised learning techniques are extremely successful and being applied, right? But at the same time, transfer learning itself applies to a supervised learning problem, but it now allows you to be able to leverage all this great work and apply it to the different domains of your choice, right? And therefore, from the beginning of time, when deep learning started bursting into the scene to 2016 to today, you'll see that any kind of, and this is just a hypothesis, and please send us a mail to disprove this statement, if you will, right, is that take any kinds of vision applications that's out there today, right, whether it's accessible via an API, right, that a company like Microsoft or any of these other tech companies are releasing, underneath the hood, you would be applying transfer learning, right? Or if you're building innovative kind of applications in your own organization, I bet you that any tutorials that you get off the internet will start off with applying transfer learning, right? And the question here is, what is transfer learning and why is it relevant, right? And so with that, we're going to kick off this talk with transfer learning in computer vision to orientate everyone to the field. And for those that's already experts in the area, bear with us. And then the second half of the talk is going to say, hey, transfer learning is not just about vision. It has a lot of commercial success in vision, right? But you really can apply it to any kind of domain where deep learning is applicable. And therefore, I'll hand it over to Daniel to start talking about transfer learning in vision.
Awesome. Thanks, Woo-Hong. Great. So I'm going to be talking about transfer learning computer vision and at different applications. I'm going to start off by giving an overview of transfer learning and the common applications. I am going to end with giving some of the more recent developments and some ways that people are using transfer learning in some interesting ways. So for those of you who don't have a background in transfer learning, I think the first few minutes will be very useful for you. And then for those that do, hopefully there'll be some interesting tidbits that you can take away at the end as well. So transfer learning computer vision, obviously there's a lot of applications we can do with computer vision. So much of the world's data is captured in images. We want to do things like understand what's in the image. We want to count things for retail or manufacturing type applications. We want to find objects. We want to do many different things with images. And how can we actually process images? So like Woo-Hong was mentioning with transferring knowledge, the concept with computer vision is very intuitive. We want to teach the computer effectively how to see using a different data set and then apply that knowledge to then a different domain. So we're teaching the computer how to see. Now, of course, there's many details and nuances to that, but that's the general concept of transfer learning. Learn that on a particular data set, a really big deep learning model, and then apply it to this new domain. So before deep learning, the reason why we're talking about transfer learning in the deep learning field, researchers took a variety of approaches to solve computer vision tasks. So to do things like understand whether there's a bike in an image or not, they would do things like try to generate features that would understand wheels and spokes and things that are about the bike. But you can imagine these features were not very generalizable to new computer vision tasks. We're just teaching the computer how to actually process and find a bike. We're not teaching the computer, or it's not learning these more generalizable features that can be then applied to different domains. So these features were not very generalizable, not very easy to transfer. Now, with machine learning and deep neural networks, we're able to actually take a lot more knowledge into these models. Now, obviously, these models are very big, and we're not going to go into the details of convolutional neural networks in this talk. But these have been shown to perform extremely well at a variety of computer vision tasks. But the problem is you need millions of annotated data points. and significant compute power, as Weihong was alluding to. So these are very, very effective tools, but they are also very hard to actually apply in practice. Even if you had vast amounts of data, are you going to have that data all labeled with what is exactly in the image, or if you're trying to do object detection, where exactly the objects are within the image? That kind of annotation on top of the data is needed in order to teach the model, and that's very expensive to collect. Now, convolutional neural networks, you can effectively think of them as two main parts. The feature extractor part, which is all the layers that are going to help generate features, and then a classifier at the end, which then classifies the image into different components. And that is, as a just general frame of how you can think about convolutional neural networks, can be helpful for thinking about how it's then applied to transfer learning. So again, it's the feature extractor part of the network, which is convolutional layers and pooling layers and all of these different components within the network, and then a classifier at the end, which is a fully connected layer, which actually does the classification. Now, if you think of it like that, it'll be helpful when we start talking about transfer learning in more detail soon. So ImageNet is a very popular data set. A lot of the pre-trained models that are available out there are trained on this. About 14 million images that are labeled, and computer vision with deep neural networks are able to do this more effectively than a human today. Now, of course, there are a lot of asterisks to that were alluded to in things like the keynotes, things like biases and how these models are developed, and things like adversarial attacks that you can do to these networks. But for a lot of machine learning applications, these models do extremely well and can have a lot of business value. So now to take that more concretely for transfer learning for computer vision, what is typically done, and ImageNet is obviously just one example data set, although it is very popular. ImageNet data set, what you can do is train a model using data from ImageNet, and then you're generating this model, and then you're applying that to other domains. So that model has effectively, you can say, learned how to see, and then we're applying that to do these computer vision tasks. Now, I'll go into more detail to talk about how you actually modify it slightly so that it can be more applicable to that other domain. Because obviously we're not going to be predicting. ImageNet has lots of different categories, things like cats and dogs and houses and chairs, and if we're trying to do a manufacturing example, for instance, of whether there's a defect or not, we can't just apply that blanketly, right? Like that model has learned things, but we need to then modify it to fit that domain. So to understand how this is working a little bit, we can look at visualizing the underlying layers. This is this really nice blog post, and the slides will be available so you can leverage this, that goes into how to do and how to look at the actual features and details within the convolutional neural networks, what they mean and how generalizable they are. Generally speaking, the earlier layers in the networks are picking up things like edges and shapes and textures, and then later parts of the networks are picking up more complicated hierarchies on top of those earlier networks, earlier layers. So neural networks are, generally speaking, they're differentiable with regard to their input. So what that means is we can actually tweak them in certain ways and feed inputs in certain ways in order to actually understand what these different layers are doing and understand the details of them. So here what we're doing is feature visualization, trying to understand about the network or parts of the network, and how we're doing that is by generating examples. And here's just one more example, and this is looking at a diversity example, so looking at how you can do not just optimization of the different layers, but looking at diversity in terms of how different images can actually, how different images in that layer actually affect it. And so you can see some data set examples here where this particular layer is actually optimizing for. So just some interesting results, and I definitely encourage you guys to check out these websites. So let's go into an example. So we have a retail website where they want to improve this website for their end users. They want to do things like if there's a certain image that comes up, they want to find certain other images and give that to the end user. They also want to automatically categorize different things, like understand whether it's a dotted shirt or a striped shirt, and not have a human have to do that every single time, because that's obviously very time consuming. So these different types of computer vision applications in a retail website seems like a very good idea, but they only have 1,700 images, for example, which they captured and manually annotated. Now we have a deep learning model that has millions of parameters. We have some decent compute power, but we only have 1,700 images. What do? We obviously can't train a deep learning model from scratch. We just don't simply have enough data to do that. So what do? We actually look to transfer learning. And so this is when I'm going to describe the different types of transfer learning and how you can actually do that. So in a standard deep neural network, which is the first row here, what we're doing is we're not leveraging transfer learning in the first row. So we have random initialization of all the layers. We have a random output layer initialization. We're not using transfer learning. We're just training the entire network from scratch on the data set that we have. This is not feasible unless you have millions of images and a ton of compute power. Now, the second type of transfer learning is called headless deep neural network, where you're going to learn using another task and do a separate machine learning algorithm. So what this means is you're going to actually use the features that have been learned on the related task, which in this case is, generally speaking, something like ImageNet, where you have a model that's trained on a related task, which is learning how to classify different images. And then you're going to use that model as a way to featureize the data set to feed into another classification algorithm. So that's just serving as a way to create features for you. The next method is called fine-tuning, which is very similar. The only difference is we're going to actually fine-tune the features, and we're not using a separate machine learning algorithm. We're using the entire neural network, but we're actually updating the weights throughout the entire network. And so you're going to train the featurization and the output jointly with the small learning rate. And then the last method that's also available is the multitask deep neural network, where you learn features or need to solve many related tasks, and you can share the featurization network across both tasks. This is not done as often in practice, but it's definitely something that's available. So to use a pre-trained CNN as a featurizer, what this means is we have that deep neural network that's pre-built. It's been built to solve ImageNet's data, to solve classification using ImageNet. And we want to use that in order to apply the things it's learned, like how to identify shapes and features and textures. And then we want to apply that, and we use that simply as a way to create features into the algorithm. So rather than creating features manually that can detect things like a spot on a shirt or not, we use the model that's trained on ImageNet, which had things like spots in those images, and we use that to feed into another classifier. And so that classifier could be things like SVM or LightGBM or XGBoost, or whatever classifier you want, and it's just serving as a way to featurize your data set. So fine-tuning, what fine-tuning is you're going to use that pre-built convolutional neural network that's built on ImageNet, but you're going to fine-tune the weights throughout the network. So this is a way to update the model to be more particular to your domain. So to give you some example results on some this texture data set, for instance, doing DNN featurization, which again is super simple in that you have a pre-trained model that somebody in the community has given access to. You leverage that pre-trained model, you apply it in this particular instance, and you just train a regular machine learning classifier on the features as a result. And so you get pretty good results. Now, in this case, fine-tuning did improve the results. So we have enough data in this instance to actually fine-tune the network, and we can see that the results have improved. And in this case, we actually use a bigger input image size and a bigger model. We're actually able to improve the classification accuracy as well. So besides doing things like different methods of transfer learning, there's obviously many other things that you can tweak within that. And to give you another example, rather than just classification and similarity, what we're doing is we're taking that input image and looking to the compare image, and we're again using it to just featurize the data set and then compare the resulting features at the end. So this is another way to leverage transfer learning for different applications. And I also, even if you have significantly labeled data, pre-trained weights can be super useful for even just initializing the network. So even if you do plan to train a whole deep learning model from scratch, it's often very useful to initialize the network. So I've almost never seen an instance where people don't leverage a pre-trained model or pre-trained weights and do some type of transfer learning in order to improve their results. So you're probably wondering now, okay, that sounds great, but how do you know which one to do? How do you know whether to fine-tune, to bother fine-tuning, or to just apply transfer learning in terms of a featurizer? So we have some example GitHub code from a colleague of ours, Miguel Fierro, and this, again, the slides will be available, so you'll be able to check out this code, and I'll go over it in a second. where he's compared 4 different data sets. And these data sets, some of these are very similar to ImageNet in that they're real-world colored data. And then he also looked at doing this by grayscale, so looking at all these images by grayscale to see whether fine-tuning was actually worth it or not. So to give you just a quick sneak peek of what that code actually looks like, this is an example of some PyTorch code where we're actually fine-tuning. So in this case, we're actually looking at leveraging that model, and in this case, leveraging the GPU, of course, because we need GPUs for this, and then looking at cross-entropy loss as our loss function, and optimizing the entire model. Now, the details aren't super important, but I want to compare against this in contrast where you're just freezing in training. And in this case, we're actually saying explicitly that this gradients equals true. We want to change that to false. And what that is doing is it's making those not be updatable. And so that's the difference in this code. Of course, with lots of different models and frameworks you could use, they'll be different. But the example is just showing you these little differences can make a huge difference in how you actually look at your end results and how long these take to train and things like that. So let's look at the results of this analysis. So in terms of the accuracy, these are the different data sets on the x-axis, and the accuracy is on the left, and the number of images is on the right, and with that orange bar. So the one really important finding from this was that the difference between fine-tuning and freezing was really significant when the source data set and the target data set were very different. And you can see this by looking at the Simpsons results. So ImageNet is based on real data, and the Simpsons is obviously animated cartoons. So pretty different domain in terms of the animation versus real world. So in the Simpsons data set, you can see that the differences are really big, where the fine-tuning results were much better than what you would get with just freezing. Now, in contrast, the data sets that were very similar to ImageNet, so for example, looking at cats versus dogs, that data set, there are cats and there are dogs in the ImageNet data. So that is very similar to trying to do a task of predicting cats and dogs. So just simply freezing and not bothering to fine-tune the network worked really well. And so the extra effort of doing that fine-tuning, the extra compute power, the extra time is not worth it in that case. And then you can see another example here where there's one example where fine-tuning was actually worse. And this is likely because the data set was so small. So if you have really small data, you might not be able to do fine-tuning, even if the domains are different enough that you want to do fine-tuning. So those are just some of the things to keep in mind. The size of the data set, the different domains, in order to know whether to do fine-tuning versus freezing. So just a couple example applications of what we've seen transfer learning used in practice for things like aerial use classification, understanding whether a plot of land is a certain type of land, doing lung cancer detection, doing things like identifying defects using drones, and then defects in manufacturing processes. And there's a nice talk that will happen tomorrow on deep domain adaptation and using transfer learning for automated poacher detection, which you can check out tomorrow as well. So those are some traditional applications of transfer learning. What I'd say is that transfer learning can also be applied in many ways, not just to help the model results. So one way that I've seen lately of how transfer learning has been used is actually really helping in the annotation process as well. So to give an example, you can see here there's many pre-trained models in the community to leverage. So not just for things like ImageNet, but here's an example GitHub where he's created a pre-trained model to identify voids in grocery store shelves. So you can see there's many pre-trained models out there. This is obviously very different than the ImageNet classification. So to seed annotations or improve annotation quality, to give you an example, in trying to get lots of images for these types of tasks, one way to do that is to scrape images off off of things like looking at Bing and looking at images that are available for commercial use. And you can see that if you search, for instance, the Japanese word for tuna, and you try to get lots of images, not all of those are tuna. And we don't want to train a model based on these results. But at the same time, can you imagine trying to scrape this kind of large volumes of data and then manually going through and updating all of these annotations, especially if you have these tasks with lots and lots and lots of different annotations? It would take forever. It's just not feasible. So the traditional method was this manual verification, where you would go through and say you want to find some waffles. What you would do is you manually go through those and find the ones that are incorrectly labeled. You learn from that, and then you predict the correctness of the class labels. Now, instead, if we apply transfer learning, and the blog post down here gives an example, gives more detail on how that's done, but what they are effectively trying to do is actually learn what a class prototype is, and effectively figure out these other ones are noise. And so how they do that is they train an embedding model that looks at the difference between the query of the image that they're looking at versus the class prototypes. And then they find out, then they train that model using the annotations that they do have, but they create this model that effectively learns label noise, and then they apply that label noise model to other classes, even though they don't have the annotations for that data. So this is a way to use transfer learning in a different way in order to improve your annotation quality. And doing these sorts of things is often makes a huge difference in business applications, looking at improving your data quality for the rest of the pipeline. Now, with all that being said, although this is very promising and there's lots of applications, I would say, and people have said, oh, computer vision, especially this like classification, it's solved. You can do it better than humans. To give you just a quick tidbit, although I know that was discussed in the keynotes as well, here's an example of a quail, and here's the difference that is applied to this image. Yeah, I can't see the difference. If you can, you're impressive. Your eye skills are good. But you apply this difference to this quail image to get this image, and the model now thinks it's a desktop computer. And yes, this was hacked in a way, done in a particular way to purposely make the model think it was something different, but still, as a human, you've learned these concepts and can tell that that is not a desktop computer. So although we are transferring knowledge in these models, it's just saying that we're not transferring the type of knowledge that humans have. So there's lots of applications for here, but just to keep these in mind. And here's another difference as well, where we're making it look like a bath towel. So with that, I'll hand it over to Weihong.
So before we switch on to the next section, what you've seen so far is transfer learning for image classification, right? And if you recap a lot of the discussions that Daniel was talking about, is that with images, you know which are the edges, right? You know that, well, if you take a bunch of these edges and you generalize it further up the stack, right, you get bigger concepts to a point when you can then do classification on it. And you say, well, transfer learning is such a great secret, and all of us should be using it in one way or another. But what about text, right? So before we get into the text conversation, let's just take a look at the different kinds of data that we have, right? Today, you look at image, or you look at a lot of the data that comes from the audio domain. Many a times, whether it's image or audio data, this work with very rich, very high-dimensional data sets. And many often, the reason why, for example, in the last example that Daniel showed, if you apply a little bit of a perturbation to the original image, the machine thinks of it very differently, is that the perturbation really changes some of the numerical values, and therefore, to a neural net, they are just numbers, right? And therefore, many a times, image and audio processing data, which is rich and high-dimensional, we often encode them as vectors of the individual things like pixel intensity, say from 0 to 255, or a different kind of color space. Or in the case of audio, you really encode things like the power spectral density and so on and so forth. And then you're able to train a deep neural net, which is really powerful to be able to then determine whatever that you're trying to classify. Now, but if you look at text in general, right? Today you read newspapers, you read a lot of the things online, you write, right? NLP systems in general today treat words as discrete atomic symbols, meaning you take a word like cat, or in this case, I see a big cat in this thing here, and they try to do different ways of encoding it, right? You could be encoding cat as some symbol. It could be an integer value. Now, and if you want to say, hey, cats, dogs as text are they're really animals, how do you then relate these atomic symbols in its original space? But how should you be even representing it? And many a times when you do this kind of mapping, it results into a situation where you might not have the rich, high-dimensional data sets, but you have a very sparse data set. And when you want to find meaning, what is the equivalent of edge and edge in an image to something like cats and dogs being very similar, right? And therefore, the question that we often want to ask is really, how do you apply transfer learning to NLP? And it turns out that this is still also not a soft task, but there's been tremendous progress made over the years, right? And so if you look at the different kinds of NLP tasks that's out there, and NLP stands for Natural Language Processing Systems, today, one of the high-value scenarios that a lot of people have been looking into is, how do you teach a machine to read, right? In an area which we call machine comprehension, or in some literature, you call it machine reading comprehension. Or how do you do natural language inference? How do you figure out the negation? How do you figure out that different words in a sentence are contextually related to each other? And of course, the other high-value scenario that we have seen tremendous progress on, so much so that today, if we're going to do this talk in PowerPoint to a different audience, like a Chinese, Korean, or German audience, we can actually do live translation of these slides. And therefore, machine translation through techniques that you saw earlier on in the keynote has made tremendous progress, because now you are now able to apply transfer learning in a lot of these domains, right? And so, hypothetically, the aspiration is really the following. If you recall this diagram that we showed as a textbook example, you really, again, want to define the learning task. In this case, one of the NLP learning tasks that we saw earlier, whether it's translation, whether it's machine reading comprehension, or anything. And you really, the dream and aspiration here, and it's already started to happen, is you really also, similar to how you download a pre-trained model for vision, you want to be able to download a pre-trained model for language, and then being applied onto the very different kinds of diverse domains that you have. And then you go on to say, well, is this pre-trained model that was trained on the original large corpus, and is this large corpus very different from my new corpus that I'm going to apply it to? For example, I could train a language model on Wikipedia, but I want to apply this to all my customer support logs, if you will, right? If there's significant difference, how can I go about fine-tuning it? What does fine-tuning even mean? What does abstracting higher level concepts even mean, right? And once we're able to solve that, then, of course, you go through the typical data science or machine learning workflow, which is then, of course, you validate the quality of the model, and finally, you deploy the model, right? And so the question here is, we talk about what does the top layer encode, and what kind of pre-training models do you have? So it turns out that today, even before deep learning burst into the scene, word embedding or word and sentence embedding, actually, if you look at any of the NLP systems that's deep learning based, word and sentence embedding is now commonly used, right? And what it simply means from a word embedding perspective is it maps semantic meaning into a geometric space. A geometric space where you're able to say the king and queen are related, or the man and woman are related in some ways. Or when you're trying to relate verbs, you're able to say walking, walk, swimming, swam. They are really related because they're the different tenses, right? And once you have done this, then you're able to apply this embedding, right, to a lot of NLP problems that you're trying to solve. And often this is done by associating what we call numeric vector to every word that's in the dictionary, and you use different kind of distance. You could use a L2 distance measure. You could use the common cosine similarity, right? And once you have this, the distance measure really then measures the differences or the semantic relationship between two associated words, right? And of course, once this is done, you can start applying pre-trained embedding models. And it turns out that today, you can actually download a lot of these different word embedding models, if you will, and in conferences like the AI conference and so on and so forth, you get lots of talk just focusing on word-to-vec, glove, and more recently, some of the innovations by colleagues from Facebook on fast text, right? And so if you look at this in perspective, word-to-vec and glove are usually what we call shallow models. And what we meant by shallow models is, if you recall vision models, you have a pre-trained representation where the first layer encodes the ages, right? But just ages alone, as we know, right, does not capture the higher level that information. And therefore, you can imagine a shallow model like word-to-vec or glove, right, with word embeddings, really need to learn from scratch, not only to disambiguate words, but also to derive meaning from a sequence of words, which the first layer is not going to give you, right? And so fast text is really an evolution of word-to-vec in the context that not only does it extend word-to-vec, but it also treats words as n-grams, and therefore now, not only can you discover words that's in the dictionary, but you can also discover unknown words as well, right? And this is things that we're not going to go into details. This is one of the tutorials from the Keras tutorial that shows you how to apply a glove model, right, on a very common problem of being able to do text classification, right, for news groups data set. And it also turns out that the other practical things that we're not going to go into details because that will take another hour is really that when you want to operationalize a lot of these word embedding models like glove or some of the newer generation word embedding models, right, are extremely large. And therefore, when you want to operationalize it, say in containers and so on and so forth, you need to figure out how to keep the containers still small, but yet being able to get the latest and greatest embedding models as and when, or even to chop them up from a practical application and deployment perspective, which we're not going to go into details. And once it's done, right, you see similar things on, hey, you want to prevent weights from being updated. Sounds familiar? And then finally, you encode this, and then you use it, or you build a really small, in this case, a one-dimensional convolution neural net to solve the classification problem. And so the point that we're trying to make here is you really want to get from being able to initialize the first layer, right, which you get from a lot of these embedding models that's out there, to being able to pre-train the entire model and being able to use this entire model similar to what you have in Vision to be able to learn higher level semantic concepts, right? And therefore, you will really want to be able to find the equivalent of the bigger patterns, the objects, if you will, right? And then have analogy in the text space. And so various kinds of exciting work has been happening in this space. In this case, this is a work called ULMM feed, when you train the language model on a general domain corpus to capture the general features of the language of choice. And then this full language model is further fine-tuned on a target task dataset, a new domain, if you will, right? And you have different ways of doing it, right? You could use things like discriminative fine-tuning, or you can do things like applying what we call slanted triangular learning rates, or STLR in short, to learn task-specific features that's unique to this domain. And then finally, fine-tuning a classifier using things like gradual unfreezing, still applying discriminative fine-tuning, or STLR, to preserve the low-level features, but also being able to adapt to higher-level features in the concepts of language. And once this is done, you can actually then start applying this in various domains. Now, the other recent one that's really exciting is really this work on Elmo. And what Elmo essentially does is a new type of what we call a deep contextualized representation that addresses various challenges, right? One is, given all the NLP tasks there, and if you want to apply a pre-trained model, you really want a kind of new technique or a new way of representing words in a sentence and so on and so forth. And being able to plug it at different stages of your NLP systems, right? Such that overall the net effect is it improves the quality of the system. And Elmo is really the beginning of that, right? And so what is also interesting is Elmo today, pre-trained Elmo models are available. Now, to train Elmo is computationally intensive, but today, pre-trained Elmo models are available. And in fact, the paper, which you get from alannlp.org, shows that if you apply Elmo to any of the NLP tasks, any NLP task, regardless of what metrics you're evaluating against, gets about a 20% boost, right? And one of the good news is with TensorFlow Hub, Elmo models can actually be easily instantiated. And here you actually see two examples of an Elmo model, one applied directly to a sentence, the other applied directly to the tokens, and you get incredible results. Now, the last piece that I really want to get to is transfer learning for machine reading comprehension, right? And so the dream is really the following. Train on a very rich corpus, right? And then apply again to news article, customer support data. Now, it turns out that in the MRC domain, Squad is one of the largest data set that's out there, right? That give you both crowdsourced questions as well as answers. And there's a lot of MRC data sets that's out there. But the point that we're trying to get to is you really want to train on a large machine reading comprehension data set like Squad, but then apply the model to other things that is relevant to your domain, customer support and so on and so forth. Right? And it turns out that there's many work in this area. I'm not going to cover all of them, but the one I wanted to call to your attention is early on, Daniel shared with you that you will never have enough training data in any kind of real-world application. And so SingNet, which is one of the innovations from Microsoft Research presented last year at ACL, really allows you to synthesize both the questions and answers. And so that gives you more training data, right? And what is interesting is this shows you the example of the quality of the question and answers that's generated, right? And hopefully this is really the beginning of all these pre-trained models, not just image models, but NLP models being available. And all of us can use that to jumpstart a lot of the commercial applications of it very quickly. Just as a summary, we covered transfer learning and application, but hopefully by the time you get out of this talk, you get a sense that transfer learning is going to help you in a lot of vision tasks, and we're already using it without us realizing it. Transfer learning for text is an exciting new domain, and we're not even scratched the tip of it. And we actually compare transfer learning applied on a different MRC approach beyond just SingNet with Jupyter notebooks that are all available to you, right? And also considered practical consideration when deploying this in a production setting, right? And hopefully these resources, which will make the slide available, will be useful to you, right? And therefore, last but not least, we hope that, hey, many of us in this room now has the tools in our hands to be able to jumpstart and leverage this hidden secret, if you will, on applying transfer learning to not just vision, but to all these NLP problems that's out there. And this is just the beginning. I hope everyone joins us in this journey. Thank you. Thanks a lot, everyone.